Hey guys! Today we're going to learn about the real number system and properties of real numbers. We're going to start out by focusing on what real numbers are and looking at some sub-classifications within the real numbers. And we're going to take a second to watch a couple quick videos that focus on the difference between a rational number and an irrational number.
Natural numbers are naturally numbers you count on your hands and your feet. 1, 2, 3, 4, 5, 6, and so on. Whole numbers are natural numbers plus 0. That's the only difference. 0, 1, 2, 3, and so on. Integers are whole numbers plus negatives. They look a little bit like this. -2, -1, 0, 1, and so on. Last but not least, not to be outdone, rational numbers are integers and fractions like -3, 1/2, 5/8, and 14.2. All natural numbers are whole numbers. All whole numbers are integers. All integers are rational numbers. Now listen to that drummer. All natural numbers are whole numbers. All whole numbers are integers. All integers are rational numbers. Now listen to that drummer. What about 4? It's a natural number, so it's also whole, integer, and rational. What about -2? Integer and rational. What about 1.5? It's just rational. What about 0? It's whole, integer, and rational. All natural numbers are whole numbers. All whole numbers are integers. All integers are rational numbers. Now listen to that drummer. All natural numbers are whole numbers. All whole numbers are integers. All integers are rational numbers. Now listen to that drummer.
You are irrational. You never end. You never repeat. You are irrational. You're just like pi or the square root of 3. Take it from me, Mr. YB. You are irrational. You never end, you never repeat. You are irrational, like the square root of 2 or the number e. Take it from me, Mr. YB. You are irrational. You are still a real number. You're just not a quotient of integers. You are irrational. You never end. You never repeat. You are irrational. You're just like pi or the square root of 3. Take it from me, Mr. YB. You are irrational. You are irrational.
So now you know more about rational and irrational numbers. So our first learning goal was to take a look at some real numbers and to be able to classify them in different ways based on these sets that we just learned a little bit about. First, we're going to take a look at this Venn diagram. And so this Venn diagram over here shows the breakdown of the real numbers. So every number that you know and that you've worked with in math are real numbers. And at some point in this course, we'll look at these things called imaginary numbers. But up to now, everything that you know is a real number. But some numbers are also irrational numbers, and we looked at that in the video. So let's first focus on the irrational numbers. There is a symbol that we use to signify irrational numbers, so we don't have to write out irrational every time, and it's the capital letter I, and it does have a little extra little slash on it just to kind of distinguish it from other I, so it almost looks like a Roman number 2, but that's the letter we use to represent irrational numbers, and you'll see that the irrational number set is all alone over here in this Venn diagram all by itself as a separate set within the real numbers. There are also some examples over here like pi and the square root of 5 and the square root of 72. Now notice those square roots are ones that are not perfect squares, and if you were to put them in your calculator, you'd see that you'd see a list of decimals that goes on and on and on, and at some point you'd have to round them. And so that's an example of some irrational numbers. Now the rational numbers are this separate set, and we actually use the letter capital Q, and you'll kind of probably see why we use Q instead of the real numbers. If you think about the real numbers as the capital R. So rational numbers start with or we use the letter Q to represent it, again with a little extra line in there just to kind of distinguish it from other capital Qs. And the rational numbers are a separate set from the irrational numbers. The rational numbers actually contain, as you can see in the Venn diagram, all of the integers, which are represented by a capital letter Z, all the whole numbers, which is a subset even of the integers, and all the natural numbers. So here are the letters that we use to represent them, and some examples to go with each one. So remember that integers are they're the whole numbers and they're opposites. So if you look at the list of integers, we've got numbers like 7, the square root of 100, which is really 10, and also negative 10, negative square root of 64, which would be negative 8. We have 0, that's also an integer, and negative 8 halves is actually really negative 4, so of course that's an integer as well. Your whole numbers are really the numbers you think about counting with and 0 added in, and so things like 0, 25ths, which is really 4, square root of 16, which is really 4, and 90, those are all whole numbers. They don't have any decimal parts or fractional parts, they're just whole numbers. And of course they don't include any of the negatives as the integers would. And so you'll see that that is a smaller subset over here in the Venn diagram. And finally, the smallest of the sets is the natural numbers, and that's actually just one element smaller than the whole numbers, because remember we talked about in the video, the song, that the whole numbers include 0 as well. Now the natural numbers include everything that we normally count with, but doesn't include 0. So things like 1, 2, 3, 4, and 5, or 10, 47, the square root of 9, and even 34 halves, which is really 17. So that first learning goal was to look at numbers and be able to classify them in within the real numbers. And so we're going to go ahead and take a look at some examples. So our practice asks us to name all sets to which each value belongs to. We're going to go ahead and use these letters that symbolize the sets, and we'll name any set that that particular number belongs to. So the first question is negative 10. One of the subsets, either irrational or rational, because all the numbers will be either irrational or rational, real numbers. And so this happens to be a rational number. It does not have a decimal that goes on and on forever with no repeating pattern. And so we would say that it was a rational number. So we want to use the Q symbol to represent that. And also it belongs within the integers as well. So it does not have any decimal or fractional belong also in the integers. See, negative 10 would actually be right here in this Venn diagram, which means it's within the integers, but it's also a rational number and a real number. So taking a look at the next example, the square root of 30. Well, I put that in my calculator and it turned out to be approximately 5.477225575, and that is very characteristic of an irrational number. It does not have a pattern, it goes on forever, and so we know that this is a irrational number, but of course it also makes it a real number, so it would be real and then irrational, and irrational numbers use the symbol I, and that's why we couldn't use it for integer and we had to use Z instead. So it's real and irrational, and there are no subclassifications with irrational. So if it's irrational, it's in its own subset of the real numbers. Now question number 3 is 1 7/9, and 1 7/9 is equivalent to 1.7 repeating. So that 7/9 part of it, that is a repeating decimal, which actually makes it a rational number. So we have real, because there are real numbers, and we have rational. Because this does have a pattern, it is rational, it just is not an integer or a whole number or a natural number. So it does have a set pattern, and so we say that it's rational. Okay, so this is your chance to try them. So what we're going to do when we have you try questions is we're going to pause the video and you're going to try these, and then we'll tune back in and we'll check to see how you did. So this gives you a chance to test what we've learned so far. So go ahead and pause the video now. All right, thanks for trying those. Take a second to check your work. And if this video is assigned outside of class, you can always make a note if you don't understand any of the questions, and you can feel free to bring them up when we're together again. Let's go ahead and move to the next page. So now that we've reviewed the real numbers, we're going to take a look at the properties of real numbers. And these should all be very familiar to you. Starting off with the commutative property. The word to commute means to switch around. It's like a French word, I guess. And so the commutative property basically says this, that in addition and in multiplication, you can switch around any operations that you do with those two operations, with addition and multiplication. Here are some examples of each. The addition example would be A plus B is the same as or equal to B plus A. So in other words, you can switch addition around. Now remember, that doesn't work for subtraction. And multiplication would be A times B is the same as B times A. So we can switch both addition and multiplication around. And it does not change the outcome. Now the next property is the associative property, and remember the associative property is that one that says you can regroup addition or multiplication in any way that you'd like to, and it doesn't change the outcome. So when we think of grouping things together, we think of parentheses. So an example for the associative property for addition might look like this. So if we were adding these three numbers, A plus B plus C, and we wanted to group A and B first together because addition is an operation with two numbers. So if we added A and B together, and then whatever we got when we did that as a sum, then we'd add C on. That'd be the same thing as if we moved the parentheses around and we said, okay, well, if we're going to add these three numbers, instead we're going to add the B and the C together first, and then whatever we get, we'll add on the A. And so that's an example of the addition associative property. Now the same thing goes for multiplication. If you're multiplying three numbers like A and B and C by each other, and say when you do an operation of multiplication, you have to, it's between two numbers. So say we grouped the A and the B together, it would be the same thing as if instead we had multiplied these three numbers, but we multiplied the B and the C first, and then whatever we got for a product, so we'd take and move the parentheses and instead group these two together first, and then whatever we got we'd multiplied by A. So what the commutative and associative properties allow us to do is just to kind of switch addition and multiplication expressions around in any way that is more advantageous for us. So if we see a particular pair of numbers that we know are really easy for us to multiply together, we'll do those first, and that just makes calculations easier. Now, the identity property for addition and multiplication is the property that just it's a property that says doing this to a number keeps its identity. In other words, keeps it exactly the same. So when you think about what you could add to a number to keep it exactly the same, so in other words, the addition identity, you might think of the number 0. Because you can add 0 to anything and you don't change it. So an example of that would be a plus 0. Well, that has to equal a, because it doesn't change a at all to add 0 to it, so that's the identity. Now, thinking about what you can multiply a number by to not change it, well, hopefully the number 1 comes to mind. And so the multiplicative identity is actually 1, because a times 1 is still a. The next property is the inverse property, which sounds a lot like reverse. So if we think about what would reverse a number under addition, in other words, maybe take it back to 0, it would be a number's opposite. So for instance, if we had a and we want to reverse it, so to get back to 0, we would add its opposite. So a plus negative a equals 0. So a number and its opposite are inverses under addition. Now, when we think about a multiplicative inverse, we think about what we'd have to do to a number, what we'd have to multiply a number by to get it back to 1. And so when you think about, say, the number a, to get 1 out of a product of a and some number, we'd have to multiply by its inverse, which we sometimes call its reciprocal, and that would be 1 over a. So the inverse of a under multiplication would be 1 over a. And a times 1 over a would give you 1. And finally, the distributive property. Now, the distributive property is a property of multiplication, and it basically says that if you've got a number, like, say, a, and you want to multiply it by a quantity of some sort, like, say, b plus c, that all you have to do is distribute that a through to each part of the quantity. And so we know that a times the quantity b plus c would be a times b plus a times c. So we're going to play the Name That Property game in the next section, and we're going to see if we can identify which property of real numbers is being demonstrated in each question. So question number 7. Hopefully that's a clear example of the associative property. You can see that that's multiplying 3 numbers and doing them in different orders. So just switching the parentheses around here, you can see that the parentheses were moved, and so now they are grouping the 5 and the 2 together instead of the 2 and the 8 together. So that would be the associative property. And because it's multiplication, we say associative of multiplication. Now in the next example, 6 times 3 minus 7, you can see that they've taken that 6 and they've distributed it through to the 3 and to the 7. And so they ended up with 6 times 3 minus 6 times 7, which is clearly the distributive property. In the next example, 7y plus negative 7y equals 0, well, that's an additive inverse. That's an example of the additive inverse. In example 10, you can see that on one side of the equation it says 3a plus 2b, and on the other side they've just switched it around, so that is the commutative property of addition. And you feel free to abbreviate as you need to. I just wrote COM-ADD, it just means commutative property of addition. And we're going to go ahead and make the next 4 you-try questions. So study the property table carefully and choose the correct property for each of the questions. And when you're done, you can tune back in to check your answers. So go ahead and pause the video now. All right, so take a second and check your answers. Be sure to ask if you have any questions at all. Now for the next couple of examples, we are going to be naming the additive and multiplicative inverse for each number. So in number 15, we have negative 8. Well, when you think about the additive inverse, we want to know the number we'd have to add to negative 8 to get back to 0. So in other words, we're looking for its opposite in terms of the additive inverse. And so the opposite of negative 8 is, of course, 8. And when we talk about the multiplicative inverse, we're looking for what we'd have to multiply this number by to get to 1. to get to 1 from -8, we'd have to multiply by its reciprocal, which is -1/8. Now, how about if the number is a fraction, like 2/3 in number 16? Well, the additive inverse is, again, just the opposite. So the opposite of 2/3 is a -2/3. And the multiplicative inverse, or the reciprocal of 2/3, is 3/2. And just to check it, you could see if 2/3 times 3/2 multiplied to 1, and of course they do because it multiplies to 6/6, which is 1. Now our final property of real numbers is called the closure property. And the closure property basically means this: a set is closed under an operation if the operation always produces an element of the same set. If an element outside of the set is produced, then the operation is not closed. So in other words, if we take two numbers and we add them and we get another number in the same set as those original two numbers, then that operation would be said to be closed under that operation. So we're going to answer some true and false questions about that. So for instance, on number 17, integers are closed under multiplication. Well, sometimes it's good to just try a real example and see if you can come up with one that doesn't work, and if that's the case, then you could say it was false. But so I think about two integers, like say maybe I don't know, like 2 and -7. So if I multiply 2 and -7, I get -14, which is also an integer. And so I think really hard to see, can I come up with any possible combination of two integers that I multiply that would not also be an integer, and in other words would produce something that maybe has a decimal that either repeats or is irrational, and I can't come up with one. So this is true. So integers are closed under multiplication. So how about irrational numbers? Are they closed under subtraction? Well, I think about some irrational numbers, some of those like square roots, like the square root of 3, let's say. And is there a possibility that I could subtract another irrational number from the square root of 3 that would give me something that wasn't irrational? Well, I can think of one right away. If I also subtract the square root of 3 from the square root of 3, I actually get 0. Well, 0 is not an irrational number. It actually is in one of the smaller subsets. It actually would be considered a whole number, which means it's also an integer, which means it's rational. And so it actually is not closed. So this is false. Now the next one is whole numbers. Are the whole numbers closed under division? Well, I thought of a couple whole numbers. And how about, like, say 20 and 3? And if I divided 20 by 3, I'm going to get 3 1/3, which is 3, not 3 1/3, sorry. I'm sorry, that's a 6 2/3, or 6.6 repeating. Well, so we had two whole numbers, but when we divided them, we got a number that was a repeating decimal, which ends up being a rational number, but certainly not a whole number, and so this is false as well. Now remember, this is called finding a counterexample. So we just come up with an example that shows that the statement is false, and so we know if it's false in one case, then it can't be true, because true means it's true all the time. So finally, odd numbers are closed under addition. So let's think of a couple odd numbers, and let's see if there's a way we can combine two odd numbers under addition and see if we can get something that's not odd. So right away I thought of, say, 3 and 5. They're both odd. So when I add 3 and 5 together, I get 8, which is certainly not an odd number, and so of course this is, again, not closed. Odd numbers are not closed under addition. So this would be false. And that's going to end our lesson for today on real number systems and properties of real numbers. So I'll see you in class.